Okay, thanks everybody for joining us in the Learning Lab 23 provided by Cruz Data Science Initiative. It's the first Learning Lab of the year. We're going to have a busy year with lots of labs planned for the future. And today it's going to be presented by Brian Russell. So I'm just going to start sharing my screen. And that's the today's presentation. I'm going to stop my camera as well. It's Learning Lab 23, Kernel Regression using Python by Brian Russell. An introduction about what is the Cruz Data Science Initiative. It's Cruz is a consortium at the University of Calgary, and it focuses on the energy sector projects related to seismic. And the Cruz Data Science Initiative is the subgroup that's focused on data science projects related to machine learning and everything. That it's we have more broad expectations in projects that are not only seismic, but any type of project related to geoscience, energy sector, and environmental. We also provide some programming training in Python, R, and MATLAB. And in the future, we're going to be probably releasing data science training together with the University of Calgary. And we also provided those learning labs. Those are those bi-weekly free webinars where everybody can join and watch live, or you can access the old labs by accessing the Cruz website, as well our Cruz YouTube channel to watch all the videos. And to stay tuned on all the events, you can go to our meetup group and so you're gonna always keep with the notifications when you're gonna have new events. And for today's, those are the hosts. I'm Marcelo Guarido. I'm a data scientist with a PhD in geophysics, and I'm the head of the Cruz Data Science Initiative. And we have co-hosting Daniel Trad. Daniel, would like to present?
Yeah, hello everybody. My name is Daniel Trad. I'm an associate professor at the Department of Geophysics in Geoscience at the University of Calgary, and working at least part-time in the machine learning problems and the union with geophysical problems.
Thank you, Daniel. David Emery, he's here, but he won't be able to present himself. He's a geophysical specialist. He's a member of the Cruz Data Science Initiative, and he's now a PhD student with us at the University of Calgary and Cruz. Brian, would like to present yourself?
Okay, hi everybody. I'm Brian Russell. I'm with GeoSoftware. I used to be with CGG, but GeoSoftware is now an independent company, and I'm also an associate at Cruz, so we're an adjunct professor in the department and affiliated with Cruz. So look forward to talking to you today.
Okay, thank you. And I believe that's my part. So I'm going to pass to the presenter.
Okay, so I just share my screen now. Oops, share screen. Okay. Okay, so I'll put this in presentation mode. Can everybody see this? Yes.
Yes.
Okay, good. Well, welcome everybody. This is Lab 23. It's a follow-up from Lab 22. If you didn't see Lab 22, which was about essentially polynomial regression, I'm going to quickly summarize it, but it is available online. So just to follow up with what Marcelo said, I'll give a brief introduction. Well, here's Daniel and Marcelo. I left out Dave for some reason, sorry, Dave, but I'm going to review polynomial regression. Then I'll look at the basis function approach, then the kernel function approach, and finally do some Python code demos. And we'll have some Q&A. And I do apologize up front if it's too mathematical for some people. I worked hard to try and cut out as much math as possible, but it is a pretty heavy topic. So if you have trouble with some of the math, I do have a number of examples that hopefully will help. So as I said, in Lab 22, I discussed polynomial curve fitting using two problems, basically. A very simple 3-point problem that is easy to understand, but it's almost trivial, but it's not, because 3 points is just enough points to illustrate the concepts. And then I used a more interesting 10-point noise corrupted sinusoid that actually I borrowed that example, or I found a similar example in the book by Chris Bishop, which I'll talk about later. So I showed that if you have n observational points and a polynomial of order p, if n is equal to p plus 1, we get an exact fit to the points. But if it's less than p plus 1, we underfit the points. And if it's greater, if n is greater than p plus 1, we underfit the problem. If n is less than p plus 1, we overfit the points. I then introduced two different regression solutions, primal and dual. And I know most people, including me, are very, very familiar with the primal approach, but a lot of people are not familiar with the dual approach. I certainly wasn't up until a few months ago when I really started getting into this subject. So the primal solution involves inverting a p plus 1 by p plus 1 dimension matrix. That is the size of the polynomial, or the number of basis functions. And the dual regression solution involves inverting a full n by n dimensional matrix, which with appropriate pre-whitening. So what I'm going to do in this talk, I'm going to expand the linear solution to include nonlinear basis functions, and using primarily Gaussian functions initially. And then I'll show how the dual solution leads to what's called nonlinear kernel regression methods, which are an extension, in fact, almost identical to the basis function approach when n is equal to p. And then I'm going to use what's called the kernel trick. I'll introduce you to the kernel trick, which creates kernel regression methods based on any allowable kernel function. And I'm going to use the polynomial Gaussian and sigmoidal or hyperbolic tangent functions. That should say discussing here, but I'm going to finish by discussing the generalized regression neural network, which is related but quite different, as you'll see. So as I discussed in the last lecture, if we have n points for two different attributes or features, and we can go with as many features as we want, but it's simplest to stay in 2 dimensions. We can put them into 2 vectors. I'll call them x and y, which each contain n points, and nx values and ny values. And in polynomial regression, we want to find a set of weights which will transform x into an estimate of y, which I'll write y hat, which is a weighted sum of the polynomials, all the way from x to the 0th to x to the p. So this represents a pth order polynomial fit, but you see it's got p plus 1 coefficients because we're allowing the bias vector, the 0th order weight. And I've written it slightly different than in the first lecture to show that the bias weight can be thought of as a multiplication of x to the 0, which of course is 1. So to perform the polynomial fit, I wrote the following, I wrote the forward problem as a matrix equation. So y is equal to xw, where x is the data matrix. So we've got p plus 1 columns and n rows. And of course, there are p plus 1 weights. And what I took you through was, first of all, the primal solution, which, as I said, most of us are familiar with. The weights are x transpose x plus lambda I multiplied times a p plus 1 dimensional identity matrix times inverted times x transpose times y. And I also showed you there's 2 ways to think of that. You can think of the first term as being the inverse of the autocorrelation matrix, and the xty being the cross correlation, or you can group that whole everything in front of the y together and call it the generalized inverse. But then I showed you there's an equivalent solution called the dual solution, which is written like this: x transpose times now x transpose x, x transpose, which is now an n-dimensional matrix, plus lambda in multiplied times y. Now, in most cases, the reason we probably don't normally use the dual solution is that it's easier to invert, especially if p is much less than n, it's much easier to invert the smaller matrix. But as I'll show you today, there's a really strong reason to use the dual solution, especially when we're working with kernel methods. So I illustrated with two problems. Both of them were simple, but this was really simple. N equals 3, just x is 1, 2, 3, and y is 1, 3, 2. And for p equals 3, the forward problem can be written like this, which is overdetermined, you can see, because it's got more columns and rows. And if you do p equal 2, you simply delete the last column, and for p equals 1, you delete the last 2 columns. So if you delete the fourth column, you get an exactly invertible problem. If you delete the last 2 columns, you get an underdetermined problem. So what you can see, this is just a very quick summary of the 3 results, where the linear solution, I think we're all aware of, is just that blue line that doesn't fit any of the points exactly. It's just kind of the best least squares fit through the points. The p equals 2 is the quadratic, which is the orange curve, which fits the points exactly, but it goes very quickly to negative. So that might not be the best solution, even though it fits the points. And then the p equals 3 solution looks reasonable if you restrict yourself to 0x equals 0 or greater, but you can see it swings wildly. It has a third root, so it swings wildly up, which probably is not a good solution. So the overdetermined solution is usually not what we want. The second was a noisy sine wave, where, again, I will skip through that. You can see that the 3 solutions are the blue line again. It doesn't quite catch the trend of the sine wave. It's just a least squares fit. The orange, which is a quadratic, might do a reasonable job, might be a reasonable job. And now, of course, the third order polynomial, the cubic, does a pretty good job, but only because its structure, it looks a bit like a sine wave. But of course, if you had 2 periods of the sine wave, that polynomial wouldn't, cubic regression wouldn't do very, very good job. Now, what I did in the last lecture, I really should have normalized the points, because you can see that as we go to higher and higher, like if I added some more columns there, I'm quickly getting way past the precision of the computer. So in most machine learning problems, especially when I started doing these kernel methods, I realized I should scale the data. So I scaled the data by subtracting the mean from the x and y values and dividing by the standard deviation, which gave this. And if you look at the x matrix now, it's a much more invertible matrix. So it's a standard machine learning practice to do that scaling. There's different types of scaling, but I like to use, subtract the mean, and I think it's called a z-score transform or z-score transform. And the results are very similar for these data sets, but what we're going to notice, what I did notice when you go to much higher order polynomial fits, if you don't scale your data, the solution quickly degenerates and gets is unreasonable. So this is the data set I'm going to use today for the sine wave. It's going to be, but I should have also scaled the this guy, but the points are so small that I didn't really need to. So really, I should have scaled them both. Okay, so before we get to the kernel method, let's look at the concept of linear basis function models. It's well explained in Bishop's 2006 book. I've got the reference at the end, chapter 3. So a linear basis function model is an extension of a strictly linear model where x is replaced with a nonlinear basis function. So the output is now a weighted sum of, now I'm going to use m instead of p, because I'm p indicated polynomial. So m plus 1 basis functions. And an example of this would be polynomial regression, where basically the basis function is simply xi sample, the ith sample raised to the j power. And when j is equal to just 0 and 1, it reduces to just the strictly linear model. Now, why do we call it a linear model, even when we use nonlinear functions? It's linear because the weights themselves are linear. So it is so it's a bit confusing. Even though it's nonlinear basis functions, it's called a linear model because of the linear weights. Now, there's several other basis functions I'm going to look at today. The one that I think is probably the best, always gives the best results, is the Gaussian basis function, which is simply phi of j at the xi sample is x of I minus some mean value or some value mu j. You can think of it as a mean or just as a sample or as a value divided by, so it's minus x minus xi minus mu j squared over twice the standard deviation squared. Okay, so that's one model we're going to use. A second is the hyperbolic tangent, which we can write like this, where the c term is simply xi minus mu j over sigma. And it's related to what's called the logistic function s of x. So you can see that the hyperbolic tangent. So actually, I don't think I mentioned hyperbolic tangent. Hyperbolic tangent is simply a scaled logistic function. So they are very similar, these two functions. And let me show you. The three curves are shown here where mu is 0 and sigma is 1. And you can see the heavy dash is the arctan, which goes from -1 to 1. These are called sigmoidal functions because they look like S-shaped functions. The s of x, the logistic function, is simply a scaled and shifted version. So it goes from 0 to 1. And again, halfway through, it hits the, so for example, for the arctan, halfway through it hits 0. For the logistic function, halfway through it hits 0.5. And then, of course, the good old Gaussian, you can see there's the Gaussian shape. So to solve for the weights, it's very similar to what we did before. We set up the problem as before, where capital phi is a matrix containing the n plus 1 dimensional basis vectors. So in other words, each row is the transpose of a basis vector. So it's got, each row has m values. So there's going to be m columns and n, where m is usually less than n, so n rows and m columns and m weights, m plus 1 weights. And sorry, I should have said m plus 1 rows because of these bias. So to solve it, we use exactly the same solution as before. We can do the primal solution, but now instead of the x, what I called x before, it's phi transpose phi, and so on. For the ridge regression dual solution, it looks like this. One thing I should mention is you don't necessarily always need that lambda term, but if it's small enough, if you need it, you really need it, because if you don't use it, it's going to blow up on you. So putting a small amount of pre-whitening lambda is always a good idea. Although for the determined solution, you probably don't need any, and you can set lambda to 0. Okay, so as I said, since m is always less than n, this is an undetermined problems, and therefore the primal solution is usually preferred, although both will give the same result. Now, by applying the polynomial basis functions that we used in the previous lesson, we get exactly the same result. So if I use that polynomial basis function, I'm not doing anything new. So let's get into something a little new and use the Gaussian basis function. So I'm going to start with a single basis function with mean mu, and I'll use a bias value of 1. So it gives me in our simple case, in our 3-point problem, you've got a three row by 2 column phi matrix. Looks like this. So x of x1 minus mu over 2 sigma squared, x2 minus mu, and oops, that is a typo, isn't it? I just realized. Let me go in here. Everybody see the typo? It's easy to do in this one. Let me fix it. So it needs a square on it. Thought I'd got all the typos fixed up, but all right, there we go. That should be, yes. Okay, that's better. So let's go and have a look at how to solve this. Okay, so I'm going to use a very small pre-whitening value of a small sigma value of 0.1, and I'm going to use mu of 1. There's a reason I picked mu of 1. It's equal to the first value, and that gives you a very simple solution. The weights are 2.5 and minus 1.5. So if we apply this at x equals 1, look what happens. We get weight 0, which is 2.5, minus 1.5, the exponent of 0, because 1 minus 1 is 0, and therefore that's the exponent of 0 is 1. So we get 2.5 minus 1.5, which is 1, which is the correct answer. However, that's the only place you get a perfect fit. So let's have a look at it. So your fit would look like this. It's a Gaussian function. So basically it's like the mean of 2.5 all the way across, and you get a little blip there for the Gaussian function at the first point, and it sort of bisects the second 2 points, but it doesn't really do a very good job on the second 2 points. So the obvious thing, so before I do that, let me show you the Python code for doing that. What I find is a lot of Python courses, or very few Python courses that I know of, really get into teaching mathematical or physical problem solving. It's usually fancier stuff that they do, and it's nice to. It actually is a little difficult sometimes, because to do the scientific programming compared with things like MATLAB and Fortran, because you've got to initialize everything. So, for example, I need to initialize all the matrices I'm going to be using, and so on. And so I'm going to, I've got n is my 3 points here, and I know m, don't confuse my m with my previous m. In this case, I mean m is going to be the number of points I'm going to interpolate across the whole line. So then for the single basis function approach, I do a loop where I compute what I call phi1, which is the exponent of xi minus mu1, and so on. Then here's an interesting little feature I discovered. The phi matrix is going to be a column stack, 1.t and phi1.t. So, oh, by the way, 1 is, you can see I define it as as simply n zeros. So, no, sorry, not n zeros, n ones. There we go. 1 equals np dot ones, which is the Python command, or the numpy command for a vector of all ones. So I stack the transpose of 1 and the transpose of phi1 into a matrix as my matrix. Then I compute the autocorrelation matrix, phi t times phi. I compute the cross correlation matrix by multiplying those, put some pre-whitening in, add an identity matrix, invert, do the generalized inverse. So I'm doing the primal solution here, and compute the weights. And then I then simply do a computation of y0 at each point. So for all those 100, in my case, 100 points. And that's what created this, this graph here. So the output, the plot looks like this. All right, so let's use two basis functions now. So instead of using a phi value of 0, sorry, a phi 0 value of 1, as I did before, I'm actually going to put a single basis function into each column. And again, look at that. I have to, it's so easy to forget the square. Luckily, in my program, I don't forget the squares. So if I don't fix it now, I'll never fix it. So let's do that. By the way, the program I'm using here is math type, which it used to come standard with all the Microsoft programs, but they stopped supporting it. So you have to buy it independently now, and it's not that expensive, but it's annoying. Every year you have to renew your license. It's a subscription basis. All right, that looks better. All right, so there's my matrix I'm going to solve for, and now again I'm going to use sigma of 0.1, and that's going to create a very simple solution. Now the weights, as you might expect, since I'm using mu1 of 1, mu2 of 2, the weights are 1 and 3, and oops, let's go back to full screen mode. So now if we apply it at x1, we get the right answer. If we apply it at x2, we get the right answer, because of course the exponent of minus 50 is very close to 0. And now we have 2 places. So look at what happens now. We fit those 2 points perfectly, but we don't get the third. So again, so here's the continuation of that earlier code. So I've already computed phi 0, 1. So now I'm going to compute phi 2, stack phi 1 and phi 2 together into phi, do my inversion, and so on, compute my weights. And now the weighted sum is y1, I'll call it y1, is w0 times phi 0 1 plus w1 times phi 0 2, where phi 0 1 and phi 0 2 are computed there in that range of 0 to m. Ah, look, I got my squares in this one. I was afraid I was going to, this time I was going to say, forget it, I'll do it later, but I did get my squares in this one. So this suggests this obvious third step where we use 3 basis functions. Now, by using 3 basis functions, notice we now have a square matrix, which turns out that doing this triple basis function solution for 3 points is identically equivalent. If you make the points equal to the, the means equal to the points, the x values, it gives the exact solution, and it's going to be exactly what we get from the kernel method. So we get, of course, with that small sigma value, we get an identity matrix. So now we get, if we plot 1, we get 1, 2, we get 3, and 3, we get 2, the correct answers. And look at that. Perfect. But it's a very, very ugly looking solution. It's much too spiky. So the reason for that is it's because before I explain that, this is the 3 basis functions. See what I've done now? I've simply got phi 1, phi 0, 1, phi 0, 2, and phi 0, 3. So I just computed that third basis function. So I think by now you see the idea. This is a very slow way of doing it, of course. So as I say, to simplify the mathematics, I use sigma equals 0.1, and that gave a fit that was too spiky. So if we use sigma equal, 0.1, if we use sigma equals 1, we get a very nice smooth fit to our points. So the key parameter in these basis function methods is always sigma. And you have to experiment with it until you get a solution that's not too overtrained. So the spiky solution was overtrained, but not too undertrained. So if I use a large value of 10, you get something that looks almost like probably identical to the linear fit. So too large a value underfits, too small a value overfits, or is too spiky, I guess you could say. So you have to find that kind of optimum value, which in this case is 1. Now, so in this example, we built the equivalent of a kernel function by letting the number of basis functions equal the number of points. Now we get to some little tougher math. A kernel function is defined as follows. It's kx between 2 points, xi and xj. And by the way, I should mention, I mean, because it's x is just a single value here, a single dimensional value. It's I write it like this, but you can also be using vectors in here. You can use as many dimensions as you want, and the math is exactly the same. So k xij, you can think of it as a function k, or you can think of it as just the transpose of the basis function times the basis function itself. So the kernel function is symmetric. as I said, xi and xj are any two training points. So we're going to actually compute every possible combination of the training points. So as I say, they can be multi-valued, but we'll stay with the 1D. So in matrix form, with the basis function approach, it looks like this, where so K is a matrix, and each term is basically in the matrix is phi of xi times phi of xj. You can see that. So recall that we've already defined the matrix of basis vectors as follows, but here's where I expanded it to be equal to the number of data points. So this allows me to write the kernel function like this, okay? So in other words, we simply do capital phi times phi transpose. Now we finally get back to the dual solution. You notice I can therefore rewrite the dual solution like this. Instead of writing it as phi transpose all the time, I can replace it with an equivalent thing called the kernel. Call it capital K. So it doesn't actually have to be a matrix multiplication. Okay, so another way to write this is like this, that the weights, instead of being the sum of m values, it's the sum of n values. And in this case, a, which is the inverse of k plus lambda I times y, these are there's n values there, and these are called the dual variables. So when we apply those weights at an unknown point, we get the following. We get k of, instead of k of xi xj, it's k at x naught xi. So we're actually applying it at an unknown point x naught, where the unknown point could, of course, be one of the known points as well. We're trying to see how well we predict it. And so this actually is the sum between the dual variables and the kernel functions. Okay. Now, above, if you look here, I'm still writing it as a matrix product. But here I'm just writing it as a function, k x naught x1. So in other words, we no longer need to know the function. Now let me show you the simplest possible case first, then I'll generalize it. So let's say our function is the linear solution, j 0 and 1. So we basically have exactly the same matrix we had before in doing the linear solution, except now we can call it phi of x1, phi t of x1, phi t of x2, and phi t of x3. And when we do the primal solution, again, we simply get two weights, 1 and 0.5. And when we apply it at x naught, it's w naught plus w1 x naught, 1 plus x naught over x over 2. So you get this solution that looks like this. And at a value of 2.5, you get you get a y value, an x value of 2.5, you get a y value of 2.25. So that's the primal solution, which we've looked at many times. The dual solution is a little different. The dual solution now involves a K matrix that looks like this. And it turns out that matrix, as we saw in the last lesson, is non-invertible. It's got a determinant of 0. So we have to use a pre-whitening, which gives this kind of these very large numbers for the A vector. But if we use machine precision and a very small pre-whitening value, you get exactly the same solution, the same weights. Now, when we apply the weights to an unknown point, we can write it like this. A1 plus A2 plus A3 times, or A1 times K of X naught X1 plus A2 of K of X naught, that should say X2, and A3 of X3. Okay, so if we apply that, we get the right value. Now, these are truncated values, but so if you plug them into a calculator, you're actually going to get the wrong number, the numbers I wrote down here. But if you use the full precision values from the computer, the answer will be extremely close to the primal solution. Now, I really haven't shown you that I've got anywhere yet because we didn't gain anything new yet. However, what this does is it allows us to compute the linear kernel matrix with the following equation. So in other words, this is now 1 plus, you can see, you can read for yourself, 1 plus x1 squared for the first, the diagonals are 1 plus xi squared, the off diagonals are symmetric. And so the kernel function is no longer a product of two matrices, but is an actual mathematical function. So I finally got to the main point of this talk, which there may have been a lot of, you may not have followed me completely yet, but this is called the kernel trick, since it allows us to replace the kernel in the dual form with any other allowable kernel. Now, here's the really neat thing. When you extend this to a pth order polynomial, all you have to do is raise that 1 plus xij to the pth power. So you no longer have to create these matrices adding a column at a time. You just plug in this formula. So this allows us to compute polynomial fits of any order. So we can go to 10th order, 20th order without having to build the initial matrices. And this is an example of the kernel trick for the polynomial kernel, but you can use any other allowable kernel. Okay, and here's the actual code. I won't go into too much detail here, but I put it in for completeness. We'll experiment with it as soon as I'm finished here. Okay, so if you look at it, well, let's talk about it. So there's the polynomial kernel. Kij is equal to 1 plus xi times xj raised to the power p, whereas in this case, I'm just using p equals 1. Then you invert it, come up with those a terms. Remember those a, there's n 8, or in this case 3 a terms, if n is 3, or n can be any number. So I'm going to show you now applying it to my little sinusoid example as well. And then this is the range of the output, and there's the number of points. And of course, when you apply it, you get the following. Okay, so here's the three fits, and you'll see it looks identical to the standard polynomial fit I was doing before, except now I'm using the polynomial kernel. There is actually a slight deviation as we move further from the known points due to machine roundoff, I think, or the fact you're using a function rather than a matrix, but it's very, very slight. Okay, and the a vectors look like this for the first solution, the second solution, and the third solution. Okay, now we'll go to look at the actual sinusoidal example, and you can see again the solution looks good. They do deviate slightly, but they're pretty close. But now notice what we can do is we can now use higher order polynomials. So all I have to do was change that value to 10, and I now get a perfect fit to my points. So I'm getting a fit that it's really good, except for one thing. It has these wild upward and downward swings at the ends of the points. So it's overtrained. It's over. We know that a polynomial function to a large number of points is always going to be overtrained. So this is an example of overfitting. So what I'll show you is a few other kernels. Let's go back to the Gaussian kernel, which now can be written like this. It's the, geez, this is terrible. I thought okay, I'll get this right. So easy to miss that square if you're not careful. Okay, but I did, it's funny, I missed it at the top, but I got it in the actual matrix. Okay, all right. So this means for the 3-point problem, you have your K matrix looks like this. So it's the difference of each of these values. And of course, I can put ones on, so each combination of values, I can put ones on the main diagonal, since the exponent of xi minus xi is always squared, is always going to be 0, exponent of 0, which is 1. And the result of applying it looked like this. So y hat at x naught is simply the sum of the n kernel functions, where the kernel functions now are the squared terms. I got my square in there this time. Okay. And so for the 3-point problem, it's easy to write down. It's simply a1 times x1 minus x naught squared over 2 sigma squared plus a2 exponent of x2 minus x naught squared over 2 sigmas, and so on. Okay, and here is the actual Gaussian kernel regression. And you can see the only difference between this and the polynomial regression is that I've now replaced Kij with, well, NP is the x of xi minus xj squared over 2 sigma. That's the only change from the previous code. It's the kernel substitution or the kernel trick. Okay, and then I apply it the same way. All right, so here's the actual result of applying the Gaussian kernel to our 3-point example. I'm using a sigma of 0.5 here. We get a perfect value and a perfect fit, and the values for A are 0.65, 2.69, and 1.64. So it's a pretty nice fit. Here's the result of applying the Gaussian kernel regression to our noisy sinusoid with sigma equals 0.5. And again, it's a better fit now, and the reason for that, it's that I'm saying than the polynomial regression, because it doesn't have those wild swings at the beginning and end. They're kind of much smoother, much more realistic. Okay, so let me do a little, tell you a little bit more about some of the other approaches. There's also a technique called the radial basis function neural network, RBFN. And this is another name for the Gaussian kernel method and the Gaussian basis function method. And radial basis functions were introduced by a guy called Powell back in 1987 to perform exact function interpolation. And then they were recognized as a type of regression neural network. They were first introduced in the seismic reservoir prediction by Shuki Ronen in 1994. And they're called radial basis function because each function depends only on the radial distance from a center, we'll call it mu I. And they don't have to be Gaussians. There's a whole series of different radial basis functions, but I always find the Gaussians work the best. So when the number of radial basis functions equal the number of points, we get full interpolation. And as I said, there's many types, but most people stick to the Gaussian because it seems to give the best results. So there's another kernel, which I'm going to talk about one other kernel today, which if you look at the books, they generally talk about the 3 different kernels, sigmoidal, Gaussian, and polynomial. And this one is a hyperbolic tangent of c times xi, xj plus b. And so you can write it out like this for the 3-point problem. And like the polynomial kernel, and unlike the Gaussian kernel, a tanh kernel involves the products of the values, not their differences. Okay, so, okay. And also I've set the mean of the tanh base. Actually, that's not true. I modified it. So the mean is actually B here. Okay, so, so again, the results are, again, you see this is identical to before, except now the phi term is the tanh kernel. And so for our 3-point problem, it can be written like this, where the output is the product of x naught times x1, x naught times x2 plus x naught times x3. And here's the code. And by now you see all I'm doing in the code is I'm swapping out the K matrix. So now it's the tanh K matrix. I do the inversion, then I compute the output. Okay. So here's the result of applying the tanh solution to, and you can see it's again a reasonable solution. And like it starts, you know, it swings to negative numbers, but it's still a reasonable fit. It doesn't go too wild. Now I should point out something really important here, that I actually changed this slide this morning because I discovered in my code and also in my explanation, I was actually taking the differences instead of the products. And what's interesting is depending, I see in this case, I used B equals 0, the mean or whatever you want to call it, this, the additive constant to 0, and C to 0.25. And what I've discovered, and I'm not even sure why yet, if you take the difference rather than the product, you can get virtually the identical results just by changing those coefficients. And I think it has something to do with the fact that difference can be expressed as a sum of products. So here's the result of applying it to our little noisy sinusoid. And you can see it again, it does a good fit. Now in this case, interestingly, I had to actually put B and C equal to 1 to get, I played around with the numbers until I got the right fit. And you can see that they look reasonable. Okay, geez, I'm taking a lot longer than I thought. Let's finish with the Gaussian, what's called the generalized regression neural network. Remember that the Gaussian network looked like this, just a summary of what we've been looking at. But the GRNN is quite different. It actually does not require a matrix inversion. It's simply the sum of the weighted, weighted sum of the input value or the observed values, y1 to yn, times a set of basis functions, divided by the sum of the basis functions. So it's normalized. So it looks very similar to the other method, but it's very different because it doesn't involve an inversion. So another way of looking at it is it's a sum of n basis functions, where the basis functions are now this xi minus x naught squared over the normalization, the sum of them all. So it can be written like this. Okay, so where I just multiply times 1. Okay, so here's the 3-point example. Now, the reason I put this in full like this, notice the off-diagonal terms are all zeros now. It's just a main diagonal, and the result looks like this. Now, here's the code for the kernel regression, and you can, or the GRNN regression, and you can see it's a much simpler code. It's slightly different here. Instead of computing K, I actually computed the numerator and denominator independently and then divided them. So just the way I decided to apply it. And here's the result of applying it with sigma equals 0.25. Now, what's interesting about this is what I like about the GRNN is it tends to extrapolate the points at the beginning and the end. And as you make the sigma value higher, you get a much steeper drop off at so eventually it just becomes almost like a square pulse. And here's the GRNN result for the noisy sinusoid. And again, a nice fit. And it, as I say, it flattens off, it extrapolates at the first and last points. So here's a comparison of all the results for the 3-point problem, and you can see that the best fits are done by the Gaussian and the generalized regression neural network. And it's obvious the blue, which is the quadratic polynomial, is the worst because it decays so rapidly to negative numbers. And here's the result of comparing all those other fits. They're all pretty close, except for there's no doubt that the worst performing one is the polynomial. Polynomial fit is definitely not what you want to do if you're using too high an order. But in between, all the other 3 methods do similar, except I would probably say GRNN's best because it extrapolates. It doesn't make it. It doesn't add some fictitious values at the end. It just says, I don't know what the answer is at the beginning and the end. I'll just extrapolate. So in review, just reviewed polynomial curve fitting. Then I talked about nonlinear basis functions, showed how the dual regression led to nonlinear kernel regression. And then I introduced this kernel trick, and I used polynomial, Gaussian, and sigmoidal functions. And I finally discussed generalized regression network, which always confused me because it seemed to be like the kernel methods, but didn't involve a matrix inverse. Could never get my head around it, and it's still hard to really see the underlying reason why between the differences. But it's an interesting approach. And in our example, we found the best results with the kernel regressions. So just one little postscript. Believe it or not, I've been working on these ideas for over 25 years. That might seem why they're pretty, if it's the first time you've seen them, it's pretty overwhelming. So I read Shuki Ronen's paper in 1994, where he and his colleagues applied the radial basis function network. About the same time, Dan Hemps and I were approached by Jim Schulke of Mobile about commercializing some machine learning algorithms. And these methods include multilinear regression, the multilayer feed-forward network, and generalized regression. And of course, that led to our eMERGE program. And that really got me interested in the connection between the radial basis network and the generalized regression network. So I went back to U of C to get a PhD. And that's where I met Jeff, right, Jeff? And it was a lot of fun. But I'm still working on it because I only recently discovered the connection between linear regression and these other methods using the dual approach. And I think there's still much more to learn. So here are the references. And again, I think I'm pretty sure for most of you that there was a lot of overwhelming material here, but hopefully if you get hold of the PowerPoint, you can work through it much more slowly at your own pace. So the Bishop book's really good. Hastie, Elements of Statistical Learning. Murphy, that's a really heavy duty book, but it's got a very nice section on on kernel methods. The original paper by Powell, Radial Basis Functions for Multivariable Interpolation. The book by Sholkoff and Smola, Learning with Kernels. Again, a pretty heavy book but it's available online as a PDF. The original paper by Ronan, and another paper, actually the Shaw Taylor. Again, it's pretty heavy, but that's where I really understood for the first time how to transform from the primal to the dual solution, because they do it with a very nice, simple linear algebra approach, which I understand better than the advanced math approaches. All right, that was a lot of material. So, and we're close to the end. So actually, let me, while you're thinking of questions, I meant to start up my Spider. And so all of these, I can supply all of these algorithms to you if you want, all of the code. And see, what have I got up here? Kernel regression methods. Okay. So let's push the little green button here and see what happens. Okay, so this was the 3-point example. And you can see, so one thing I didn't show you is what happens here when we change the actual pre-whitening, not the pre-whitening, sorry, let's go down and look at kernel regression. Change the sigma value, sorry. So let's see what happens if we go into Gaussian kernel regression. I'm using a sigma of 0.5. If I use a sigma of, let's say, 1, let's see what happens. So it's still fitting. So let's try another. Let's do 2. See what happens. And you can see that. No, that's not it. Well, it always seems to be fitting quite nicely here without, regardless. Let's see the 10. See if I can really. Oh, I didn't talk about logistic kernel regression. Oh, that's not. Gaussian kernel regression always seems to fit. Well, let's try. That's interesting. Gaussian. Okay, let's go and let's go. Oh, one thing I wanted to show you. I don't know why that's always. Let's do the generalized regression neural network and change sigma in there. Actually, that was the one that if I use a very large value. Oh, yeah, it's basically flat now. So 10 is way too large for this. So let's use 2. Yeah, again, so you can see that as you use large sigma values, it starts to diverge. Anyway, so if you get the code, you can play around with these different parameters and see what. Well, actually, let me just do one other one. Kernel regression methods for the sine. There we go. Now I did also the logistic regression. The reason I didn't talk about it, I could never get a perfect fit using logistic regression. So it appears that actually that's not entirely true. If I put the mean back in, I get a much better fit with logistic kernel regression. It's probably got something to do with the fact the tan H has, goes between -1 and 1, and the logistic kernel just goes from 0 to 1. Okay, I've been doing all the talking. Is there any? Let me check to see. Let me stop screen sharing.
Yeah, I think we have a question.
Okay, time for some questions. Yeah,
it's in the Q&A.
Okay. So sharing file. Yeah, you're going to put them in the GitHub. I've got to send them to you. You're going to put them in GitHub, right?
Okay, perfect. And there is a question. Thanks so much, Brian, for the presentation. I have a question about pre-whitening parameter. You choose very small number in kernel regression. Does increasing pre-whitening parameter affect the results more in kernel regression compared with polynomial method?
Okay, pre-whitening I don't think has as big an effect as the sigma value. What I generally find with pre-whitening is it really, putting a little bit of pre-whitening solves the problem usually. So I would recommend always starting with a very, very small amount of pre-whitening. And if your problem is still not behaving, then increase the pre-whitening. But in general, I would always recommend putting a small pre-whitening. It almost appears that the big difference is between no pre-whitening and a very small amount. A very small amount will usually stabilize the solution. Daniel, do you have any thoughts about that?
Actually, yes. But it's a bit complicated to put it here. One thing that I experience, you see, when this method, I think, is quite related to generalized least squares, and that's something we use for things like the sparse inversion, right? Like Brian and I discussed this. So I found that when you use something like the kernel method, you can regularize differently. That is basically that. Let me try to simplify as much as I can. When you do regular inversion, you have to use a non-constant diagonal to do a sparse inversion.
Okay, you're talking about something beyond pre-whitening now, right? Yeah.
Right. So that is the thing. When you do what you're doing now with the kernel, what happens is you can convert that non-constant diagonal into a problem where the diagonal is constant. So I guess the simplest I can answer is differently. It will, I don't know if it will affect more or less in each case, but what I can say is that affects differently, and you can use that in your benefit. Right. So you can make your regularization to work differently with the kernel that it will do without using the kernel method.
I understand. Yeah, I think the thing of today, I was using very simple problems. So just our diagonal pre-whitening works great. But when you're working with real data, when you're doing things like Tarantola does, you need different values in that code. In fact, you can even have off-diagonal values, right?
Right. Exactly. Yeah. We use that kind of trick of playing with the kernel, although we didn't call it like this, right? But I think I would say, yeah, generalized least squares inversion is a parallel development of this. I don't know how. I don't know now on the top of my head how different it is. But the point is that people use that to change the way your regularization affect your solution when you stop your iterative algorithm earlier.
Okay.
That's the kind of the simplest I can put the answer.
And this, and of course, all my solutions here, I was not doing any kind of iterative inversion. I was just doing straight in, because the matrices are quite small. But yes, in a normal case, when you have real data, thousands of points, you'd want to do some kind of conjugate gradient or gradient descent, right? And that's going to affect the
right.
Yeah, the main. I mean, in some everybody's going to laugh at this. Some this was oversimplified today, although I don't think the math was that simple. But you know, when you get to real data problems, you have to be there's a lot more to take into account. I was really trying to illustrate today the concept of the dual method and how the kernel comes into it. And I know, Daniel, you got some ideas about maybe applying this to inversion problems, right? The kernel method.
Right. Yeah, and I'm sometimes it's uncertain whether we are already doing it or not.
Yeah.
Without knowing it. Like this is the same with machine learning, right? It reaches into a lot of things that we have been doing over the years. Now, what I never saw before, a clear explanation when you go into machine learning and they start touching into the kernel trick, that in the context of machine learning is for the first time where I saw the explanation that you are actually saving all these additional computations where you don't actually have to convert each point in your data set with the kernel, because all what you require is a dot product between them. And that's what you showed today. But I think in some context we have been using it. It's just it's hard to tell.
Yeah.
So it's a lot of
what I like about this method is it reduces all the way down to the standard linear regression problem, right? Mm-hmm. And it's just one line of code you have to change. You can go from you know, any of these methods. In fact, there's a number of other types of kernels I didn't talk about, but the three main kernels people do talk about are the like say the Gaussian and the polynomial and the tanh. So,
right. I don't know if you mentioned this, Brian, but you probably did it, but I may have missed that. For the function to be a proper kernel, there has to be some mathematical condition.
Yeah, I didn't get into that. It's well explained in a lot of these books. There's some real restrictions. Bishop has a big list of, and he starts showing the relationship between radials and radial functions and just you know, product or dot products or whatever you want to call them. And yeah, there are some, and that's where it really gets complicated when people talk about all the mathematical restrictions on what makes an allowable kernel. And in fact, the reason they use the tanh, for some reason, the logistic function is not an allowable kernel. I was experimenting with it, but and it gives good results sometimes, but it's mathematically not allowable. So there's some restrictions on it. No, I'm not a true mathematician. So for me, the big point was to see how these simple tricks can be applied, and you know, I'm looking forward to seeing if we can apply it to some real data examples. So I see a few, you know, Jeff. Now, can people speak, or do they have to write Q&A?
I have to give the permission to them. So you wanna?
Well, I'm just wondering if anybody, like, you know, I see Jeff Grossman. I see actually I see that Marco's no longer there, so that's right. A few other people. Anybody?
Hey guys, can you hear me?
Yeah, I can hear you, Jeff.
Oh yeah, great talk, Brian, and
thanks.
Good discussion, Daniel. I'll see.
Good. So nothing.
I guess.
No specifics. Okay, good.
I don't know if I'm just part of my brain's in la la land, I think, but I'm just wondering, like, all the examples you showed, like when we had good fits,
yeah,
the solutions contained the points that you were trying to fit to. And I guess in the real
world, those were the fits, and if it went through the point, it meant it fit the point, right? Yes.
Yeah. So, like, of course, so you're alluding to real data. So real data has noise in it, and you don't necessarily want to
Exactly.
fit
You're
for the
never going to
data.
get a perfect fit to real data. And
Yeah.
I definitely need to extend this to, but wait a second. I have, the point is I've given many talks extending this to real data, because we use in our emerge program, we actually have both, well, all three of those methods. We don't have the polynomial regression. We've got the multilinear regression, we've got the radial basis function method, and we also have the generalized regression neural network. So I've got multiple talks that show how to apply it to real data.
Yeah.
The problem I find when you're applying these things to real data, you see some pretty pictures and that's it. You don't really understand what's happening. And that's why I went to these very simple 3-point and 10-point problems, to really try and understand what's happening at the level of the algorithm.
Yeah. And just looking at like the example with the sinusoid is interesting, because if you knew nothing about what's sort of driving the data, like if you knew nothing about what the patterns were, which solution would you choose, right? I mean,
well, and I certainly wouldn't choose the polynomial, because it's got to be a polynomial. So a lot of people are saying, told me that the generalized regression neural network, which is also called a Parzen estimator, it's got a lot of different names from statistics, seems to be the most robust. We've always had excellent results with that. Now, one thing I didn't compare it with are the deep neural networks. In Bishop's book, he has a very nice section on how this relates to the deep networks. They're never going to be exactly the same, but they're close. They're close. So
yeah. Well, I guess I'm thinking more from a hands-on perspective. Like if you're actually asked to solve a problem, and say somebody knew that there's a sinusoid underneath that data, but you didn't as the problem solver.
Yeah.
So you wouldn't be able to say which is the best solution, right?
No, you wouldn't. Well, you could do if you knew what the exact solution was. And by the way, there was noise in that problem. That was a noisy sinusoid.
That's true. Yeah, you're right.
Yeah. So, but, by the way, we should probably let Larissa have a question too.
Okay.
Thanks, Jeff. Yeah, we can take this offline and talk. It's
for sure. Yeah, I don't think I was saying what I meant to say there, but thank you anyway.
Send me an email.
Okay, well. Cheers.
I think we have one more question that Alireza wants to ask.
Hi, Brian.
Hi.
Hi, thank you so much for the great presentation. I appreciate. Wondering what is the the very first immediate application that you're trying to apply this kind of method on?
Yeah, and I was very remiss. In not telling you the big picture. The big picture is that, as I was telling Jeff, we have these algorithms. Most of these algorithms have been coded up in our emerge program, and that the application is predicting reservoir properties from multiple seismic attributes. So the differences are the X values are multidimensional seismic attributes, and the Y values are, the training values are some kind of reservoir parameter. I don't know why I didn't make a bigger point of that, other than the fact I assume that is a given, that I'm trying to understand the simplicity or the simple parts of the more complex things when we apply it to predicting reservoir parameters. Funnily enough, a couple of years ago, maybe it was 2 years ago, I submitted a very similar paper to the SEG, where I actually showed real data examples as well as the theory, but it wasn't the dual method. It was before I'd really come to terms with the dual method, and the paper got rejected. So it's
yeah, I mean, it seems to me that anywhere that we have any kind of an inverse problem, these kind of methods can be applied. It doesn't have to be even seismic. It could be any kind of application.
Yes.
But even for the seismic, full wave inversion, tomography, any kind of the inversion approach can be targeted by this kind of method. Is that the general statement?
Yeah,
Right
yes
statement?
and no. Some of the methods you brought up there are actually deterministic or physics-based methods. So this is not a physics-based method. So there is a paper I published a couple of years ago on the Leading Edge, which compares a very simple decon problem, which, well, I could say decon is a physics approach, it's based in physics, with the neural network. And in fact, that was the whole point of my follow-up paper to geophysics, to SEG. And it sort of gets back to what Jeff was asking about, if you knew the underlying problem, how does it compare? So yes, it's similar to deconvolution. It's similar to what do you want to call it? Migration or tomography. But the thing about those problems is they have actual physics solutions, right? With the machine learning is not a physics solution. It's a mathematical solution. It's trying to fit a problem using these nonlinear basis functions.
Yeah, but these days, everybody kind of talking about the hybrid approach, that we can actually use kind of physics behind all these problems to train all this machine learning approach. That I was kind of thinking this could be really a generalized kind of problem. Yeah,
my colleague John Downton has published several papers on that, and his idea of the hybrid approach is that you never have enough data points, so you can for these problems. We don't have as many data points as they do in most other machine learning applications. So you generate the data points using things like physical models. So actually putting in rock physics constraints and that kind of thing. But at the end of the day, the actual machine learning algorithms you're using are not, they don't know the underlying physics. They're just trying to fit a solution based on functions.
Sure.
Weights and functions. That's all they're using.
Yeah, and just one last question. Between all this platform for using Python, Spider is the easiest one that you find to work with?
Yeah, I'm kind of a prehistoric. I mean, if you really want the real goods on how to use this, take courses by Daniel and Marcelo, because they get into. No, I would say I really should be using Jupyter, and the Jupyter notebooks are really the way to go. And I'm a pretty crude programmer. I like to just write simple Python programs. And as I said earlier, I like to figure out how to solve physics and math, or I implement physics and math solutions using Python, which is something Python's much more general than that. It's actually quite difficult to solve mathematical problems. Would you say, Daniel or Marcelo?
Yeah, I like actually
to do MATLAB.
Their ideas, as well, because I have an idea. I mean, I have been coding in MATLAB in the last 20 years, and I'm just hard time. Which platform for Python is the best?
Stick to MATLAB if you're happy with it. The only reason to go to Python is it's become the flavor of the month or year, and it's easy. It's cheap. It's free, right? So, but yeah, I can do all this programming. What takes me a couple of hours or days in Python, I can do in minutes in MATLAB. So.
Yeah, the same here.
Yeah, I think if I can comment on that.
Go ahead, Jeff.
I really like both, but I would probably spin up MATLAB if I was doing linear algebra.
Yeah.
But if I was throwing data around and reading and writing and manipulating rows and columns and doing all sorts of data cleaning and that kind of stuff,
it's Python.
Then I would go for Python, right?
Yeah, you're right, Jeff. And the big advantage of Python is people have written all these algorithms. You don't have to write anything from scratch anymore. You just go to a TensorFlow or
Pandas.
They're all written. The main purpose of this talk today and the last time was to show you can write your own scripts. And I personally have always believed if you can write an algorithm, the best way to learn is to write a program, because the program doesn't lie. It either gives you the right results or it doesn't, right? You can think you know something by writing a few equations down, but until you actually program it up and see the results, you're not sure if you've got it right. And even if you use a canned program that's something in TensorFlow or something, you're not quite sure. There may be some bugs or, some things you don't understand.
Yeah.
Great. Thank you so much.
We're going way over here. Sorry, guys, Marcel. But thanks for staying, Jeff and Larissa.
Yes.
Thank you.
I would like to end the session. So I'm going to share my screen. So I'd like to thank everybody for joining us. And I guess that's
Thanks,
it.
Lucas.
Tune in on our social media for the next events. We're going to have another one in 2 weeks. And thank you. And see you soon.
All right.
Hey, thanks. Take care, everybody.
Thanks, guys. Thanks, Jeff. Thanks for coming.
Bye.
Thanks,
Thank you.
Larissa.
Thank you.
Thanks, Paloma. All right.